Welcome to standing wave problem number 2. Consider a standing wave on a string with a frequency of 16 Hz at the second harmonic. So F2 is equal to 16 Hz. If wavelength is 0.16 meters, find the distance between nodes. So here they're giving us lambda 2 is 0.16 meters, and we want to find the distance between nodes on the string. So we can draw the string, and it's our second harmonic, so n equals 2, so we're going to have 2 antinodes. And we want the distance between nodes, which is here to here. I'm going to call that D. So if you notice, this whole wave pattern is one wavelength, right? Our wavelength looks like this, and we have one full wavelength. So D is half of a wavelength. D equals lambda over 2. Let's just put in our wavelength right here. Divided by 2, and we get 0.08 meters. In part B, we're asked to find the speed of the waves that make up this standing wave pattern. So V is equal to lambda F, and we're at the second harmonic, and now we're just going to plug in our numbers. We have 0.16 meters for our lambda, and we have 16 Hertz for our frequency, and that ends up being 2.56 meters per second. Remember, Hertz is just 1/seconds. In part C, we're asked to find the frequency of the fifth harmonic. So Fn is equal to n times F1. Here we have n equals 5. So F5 is equal to 5 times F1. But we don't actually have F1, we have F2. So we can do this again. F2 is equal to 2 times F1, right? If we just take this and say n equals 2, we'll get that. So we can solve for F1 here. F1 is equal to F2 over 2. And then let's plug this into the F1 there. F5 is equal to 5 times F2 over 2. That's 5 halves times F2. 5 halves times 16 Hertz, and that is 40 Hertz. So in this problem, we are given just the frequency of the second harmonic at first, and then the wavelength. From the wavelength, we were able to find the distance between nodes. We were able to find the velocity if we multiply our wavelength times our frequency, and then we're also able to find the frequency of subsequent harmonics given our F2.